Good afternoon, everybody. So let us start. Today is September 30th, last day of September 2021, and today we will discuss a challenging topic: red black trees. Okay, so as a preparation, we started with Avl tree last week, right? Last week we discussed Avl tree, right? So what is an Avl tree? An Avl tree is a height balancing tree, right? That it balances its height. So in case we started we started with a BST or a binary tree, okay, BST that was growing linearly. Not, we expect that a binary tree should grow logarithmically with log base 2. It will be balanced, height balanced. But we found with some example that what is taking so much time, that a BST may grow linearly. For instance, we found that if we have some elements, for instance 2, and the next element is 3, and the next element is 5, it will go right side, right? So BST, we are trying to make a BST, but we got the first element 2 and the second element 3, so the second element go on the right side. So this side is left empty, this side is empty, this side is null, and so this side is not is growing linearly. So right, then height will be n, but we expect for a BST we expect height equal to log of n, right? So but this is a problem. We started with this problem, right? So in order to resolve that problem, so there is a concept of Avl tree, right? So in Avl tree, so let me do a quick search. You need to remember the concept of Avl tree to understand binary red black tree. So in Avl tree, for instance, we got 2, then we are fine. Okay, and then you got 3, so then 3 will be the right side of 2. Okay, so in Avl tree, what are the properties of an Avl tree? The distance, height between left and right subtrees is maximum 1, the difference, right? So in that case, what is the height? So this side is null, for this side is null, so this is symbol for null. Okay, and this side is height is 1 and this side height is 0. Nothing means 0, so we should not give it, so don't, better just keep it. Null means keep it empty. So as soon as we encounter 5, so we encounter 5, so this is a problem, right? What is the problem? So this side has height 2, right? Yeah, please speak up with me. For this lecture and the next lecture for this week, please talk to me. So what is the problem here? Height difference is 2, right? Here actually, so it's 2. So this side is 2 and left side is 0. So that is a problem in Avl tree. So in Avl tree, we want to make it balanced. So height difference we want to maximum make it 1, either 0 or 1. So what do we need to do in this case? We got a right and right. We got 4 rules, right? In Avl tree, we got 4 rules. What are the 4 rules? We need to remember it quickly. Please help me. Yes, if we get right, then rotate left.
And left, you rotate right.
Yes, thank you. And then yeah, we need to remember all of the 4. Okay, and 3 and 4 are difficult, but I made them easy. So rule 1 Avl Tree rule 1. So for right rotation, make left. Okay, for instance here right, so do a left rotation. That means left rotation, it is a string. For instance, think about a string. So these are ball. Okay, so then 3 will come on the top, and then 2 on the left side and 5 on the right side. Then it is balanced, and then it is an Avl tree. Okay, now so 2 over here. Okay, so if we encounter, so let me remove this. Sorry, we need this one. Okay, so let us make it 4. Okay, let us make it 4 instead of 3. Let us make it 4. So 4 and then 2. We got 4 and then 2 and then 5 over here. Okay, so then rule 2 was for left we make a right rotation. For instance, if I get 4 and then 2 and then another 1. Okay, so then left we do right rotation. Then it will go 2 on the top and then 1 in the left side and 4 on the right side. Okay, and for instance this is rule 2, and rule 3, let us think that we don't have this. For instance, we don't have this. We got 4 and 5, and then left one, next one we encounter 3. So 3, we are over here, right? 3 will go here. So this will make a problem, right? So anytime you face a problem unbalanced, you need to make it balanced. So here the left side, this left side is height 0, and then this side is 2. So this is right and left rotation. So case 3, for right and left, I said make it like this and this. Complete the triangle and move and make it. So then that means it will go 3 will come over here, and then 4 will be here, and then 5 will be here. So how do we express? We say complete the triangle and swap. Write it in your language. Okay, how do you remember that? So I said complete the triangle, so I'm moving from here to here. So this is pretty triangle, right?
We could use different colors for,
yeah,
I think
that's a good idea. Yeah, thank you. So if I said this is move over here and then here. Okay.
So that's where the 3 moves?
3 moves to 4. So 3 will move at position 4. Okay, and then these 4, originally just 4, will come over here.
But 4 is greater than 3, so shouldn't it be on the right node?
Yeah. Yeah, so that is a problem. I did a mistake. So 4, 5. So okay, that will be like this, not 5. 5 will not work here. Actually, if I have 4 over here, and then instead of 5, if I have 6 over here, okay, and if this is 5, okay, now it will work. So the concept is that, so now it is work. I have 4 over here, and then 6 over here, and then 5 encounter 5. 5 will come on the left side of 6, right? And then in that case do this, and in that case 5 will go over here, and then 4 will come over here. 4 will come over here. Then this is 6. This is 6, and this is 5. Okay. So here the concept is that it was going to be make the triangle. Then in programming you need to do 2 rotations. In the book you see that there are 2 rotations. The book says that you need to make like this, 4 and do right rotation, and then say 6 and then make 5, and then 1 rotation. Then we got right, then we need to do this 6 5 this rotation. You got 6 over here. It's 4. This one is 6. This one go 5. The book says something different. I cannot remember because I did not understand even from the book clearly. I remember this way. It works better. Okay, and the rule 4 is that if you have rule 4 is that similarly if you have left and right, then complete the triangle. Same thing, triangle and swap. This is my way. I remember this way. Write in this rule 3 and 4 in your own language. How do you remember it? Okay, you will see that is something you can write that you remember. Okay, so my goal is today is to start with a different kind of balance tree, height balance tree, that is called red black tree. Red black tree, it is a guaranteed binary search tree. That means it's a binary search tree that will guarantee the its height of logarithm height or pretty logarithm height. Okay, so we started from the book. We saw that in the book it has a, this is an example of red black tree. So red black tree, for instance, all of the nodes it contains in addition to data. So we know that in a BST a node contains head, right, or parent, and then left and right, left child and right child, right? These references it contains. But in red black tree it holds another extra property, that is ray, the color of each node. It contains an extra property, so that it takes some extra memory. Okay, then the color must be either red or black, nothing else. Okay, and these are the properties. There are 5 properties in red black tree. First one, every node is either red or black, nothing else. Second one, the root is always black. Okay, and third one, every leaf is nil and black. So we know that this is unimportant actually. So this is not too much important because every nil node is black, and every leaf node, the 17, 30, 38, this is 40, right? This is a binary search tree. Leaf node is nil and black. I will upload this slide in D12 after the lecture. I got this from internet. Maybe there are some mistakes, or I will make it easy, then upload it. But let's get attention to that. And number 4 is the most important. Is the most important and problematic feature. Okay, if a node is red, then both its children are black. Okay, so, and the last one is for each node, all paths from the node to the descendant leaves contain same number of black nodes. this says, okay, let me give an example, solution example. So this is black. You see the circle black is black and circle red is red. Okay, black. So if you go through any path from root to any leaf, the number of black nodes will be same. So from this side is 1 and 2, right? This route, in this route, now how many 1 and 2, right? This route. And
So
from
you
this
don't count the nils?
no, so let us forget, because nail, everything has nail and always black. So just forget about, for simplicity you don't need to. So if you count nail, this is 3, 1 2 3, right? And this is 1 2 3. So just forget about the nil. It's always black. Nil is always black. So just for simplicity, forget about, let us keep about nil or leaf and look at actual nodes. So then this side, how many black? 1 and 2. And this path, 1 and 2. And from this path, from this to this path, 2. And from 1 and 2 here, 2. And from this path, 2. So this is a red black tree. So in any case, in any path, all of the path will have same number of black nodes, right? Okay, the two things that, for instance, from here, so this is why I said that these last two properties are, this number 4 is the most difficult, and then another one difficult is this one. These are the problematic, because it is simple that all leaf will be blank and black. Simple, right? Root will always black. It is simple. But this one, it says that if a root is red, then both children are black. So what it does not say? It does not say that, how about if a node is black? It does not, there is no condition on black node, right? If a node is black, then there is no restriction. You see that number 4 implies that if a node is black, then there is no restriction. Maybe the either children can be
So either red or
black or red. Okay, but the restriction is only this one. If it is red, then both children must be black. And whenever you insert, you make a,
So you're trying to say is that the converse of that statement does not apply.
yes,
It's one way.
yes.
Okay.
Okay, so that you remember that if its converse is not restriction, not a restriction. Okay, so please give a focus on these 5 properties. Okay, of a red black tree. And who can tell me? So do not look at this and then tell me loudly what are the properties.
Head is black.
Okay, root is black. Okay, one. Then what is the next one?
For each node, you
For all leaves are black.
The knolls are black.
Okay.
for each node, the path to all of its leaves contain the same number of black nodes.
Yes. The last one. That fourth one. What is the fourth one? Who can tell me the fourth one?
If a node is red, then its children must be black.
Both. Both children must be black. Okay? Yeah, both children must be black. There is no exception. But another way you can see that if a child is black, then we don't worry. Okay? So it seems to be simple, but actually, whenever we will see that whenever we create, we make a red black tree, the problem will come with property 4 and 5. And we have to, every time we have for an insertion or deletion, and whenever we want to, in algorithm, we check, always check the condition, all of this condition. But I know that problem arises 4 and 5. Okay, so now let us start to make a red black tree. But here, this is in this page, this says that whether it is a red black tree or not. We saw that it is a red black tree, right? Okay. So that one thing is that if you see a tree with red and black color with node, it does not guarantee that it is a red black tree, right? It must maintain all of these 5 properties, and you have to check all of these 5 properties one by one. Okay. If any of these fail, then it is not a red black tree. It is a tree, but we don't know what kind of tree, but we are not concerned for that. But we are for sure that it is not a red black tree. So a red black tree, it guarantees that its height will be pretty log to n, or 2 log at most to n plus 1 number of nodes. It with an internal node has height at most. We don't need this proof. Okay, so let me go with this one.
What was it? Height at most?
I'm coming with this. Okay, so now there are 2 rotations. I'm coming. So the 2 operations, main operations, insertion and deletion operation for red black tree. But before I go to insertion and deletion operation, we need to understand rotation. There are 2 kinds of rotation. It's right rotation and left rotation. Okay, there are 2 kinds of rotation. We need to understand one more thing, some extra thing. Okay, so when we discuss Avl tree, right? So when at the time we build an Avl tree, okay, it becomes balanced. It enforces it restricts to be balanced, because every time we insert, either we apply one of the 4 rules, right? We saw that in Avl tree. So after building an Avl tree, so it will be automatically, while building an Avl tree, it will be automatically Avl balanced. But a red black tree does not work that way. Okay, so the problem is that, for instance, in our Avl tree, we saw that there are simple rotations in Avl tree. We found that 4 rotations, right? 4 rotations. One right, and another number 2 is left. Another number 3 is right, left, and another one is right, left, left. Yes, and another one, number 4 is left, right. And all of these cases, the nodes were single nodes, just nodes. But here in Avl tree, we may need to rotate a branch. Sorry, in a red black tree, we may need to rotate a branch. Why do we need that? Since every phase we need to ensure color. We need to check the color, right? So if there is a disorder of color, then in order to maintain the color and number of black color nodes in every path, so we may need to sometime rotate the whole a branch, not a leaf. In Avl tree, we saw that we move only leaf node.
But doesn't the color of the branches not matter? And why would we need to rotate?
Yeah, this is always matter. Colors is always matter. This is why this is a problem. So every time you move, we need to check colors, and then before that, let us start with this with simplicity. So there are 2 rotations. For instance, it's called rotations, means left rotation and right rotation. Okay. For instance, the right child, so assume that for a left rotation on node X. What is node X? This is our node X, right? Yeah, give attention over here, please. Everybody, please give attention here. It is difficult to understand. So we wanna, for instance, here on node X, we wanna make a left rotation. Think about that. It's all of these are string. Okay, this is a string. So this is a string or flexible string, and this string has, for instance, empty. Okay, so then we want to move left rotation, left. So that string we want to do like this. Okay, right now it is balanced here, right? For instance, this is floor, this is our roof. For instance, it is tight over here. So if you want to make a left rotation, then it will not be tighten here. So tighten over here will be that here. Then we want to tighten here, different color. So instead of here tightening here, we want to tighten here, so that if you make a left rotation, then it will be hanging, X will be hanging, right? Think about that. These are string, these are balls hanging in a roof. So then if you move it, then this will be hanging, X will be hanging, right? And then Y will become on the middle. So this is why Y will become in the middle. So then it is tightened maybe in the floor, in the roof. And then X will be here. So then X will come with its children, its child, alpha. It is alpha, right? So the X will come with alpha. Okay, and then when it is rotated, then this will be untied. So this link between X and Y will be untied. This link will be broken. This thread will be broken. Okay, so this is the broken thread. Okay.
Well, it's not broken when it's done, so I mean they're still connected in the second
Let me see. So if we want to tie here, so for instance, let us think that it is tight right now here, holding here, right? But if we want to move left, then it will be tight here. So if we tie it here, think about that, what will happen? This one will go, so this line will go parallelly with this block, right? Or it will have, actually it will have three branches. A BST cannot have 3 branches. You see that? If you try, this is tight right now here, right? So every node has 2 branches, right? But if you say that just hang on here, right? Then what will happen? So it will have 1, 2, and 3 children. That is the problem, right?
Okay, yeah.
You understand?
Yeah.
So that means we need to untie or break at least one thread, right? So which one will be broken? This one will be broken.
The one from X to Y.
The one from X, that is, it will be broken. So that one is here, right? What others? It is not working. Okay. This pen is not working. So this will be untied, right? So then what will happen? So this, so we need to actually merge these two. This one and this one we need to merge. How it will be merged? So this one will go here. Okay, the beta will go with X. Okay, then we need to merge this one, this merge one. So then beta will go with X as the right side. Okay, it has already left side. It has X has already alpha in left side, right? It has empty only right side. So this beta will go on the right side of X. So then it will be hanging here. Now it says that it maintains a BST property. All nodes has 2 children, right? See that? You see in this case alpha, beta and gamma, these are leaves. Now you understand?
I'm do we know that beta is not less than both x and y?
Okay, so in this case, since it is the good question, okay, but we know that this is the BST. So in a BST, beta is always greater than alpha.
Well, doesn't beta just have to be less than y?
It is less than y.
Yes.
Less than y, but greater than alpha.
Okay.
So it is less than y, but greater than x.
Okay.
Right? So it is greater than x, beta is greater than x, but less than alpha. So it is maintaining BST property. You understand?
So that's why gamma always stay on the right side.
Sorry?
So that's why the
Gamma?
yeah.
Yeah, gamma is greater than y, so it will.
That's why it's
Yeah.
remaining on the right side.
Yes.
Okay, so like the BST property is not only the child, but the entire
subtree. In
Okay.
order to be a BST, all nodes should maintain properties.
Okay.
There is no exception. That is saying.
So B should definitely be less than x on the
Yes.
BST property. I mean greater
Yeah.
than x.
Does anyone has any other question? Do you understand this? You may. So if you don't understand this, you can do a practical at home. You can put a ball. In the ball, take some ball or marble or something. Okay. Or if you hang a paper, take some paper and then tie on wall with some thread. Okay, and do that. So initially think that it was tie here. It is tied in here. We're hanging with x, but we wanna move is here. So then we wanna hang with y. So then what will happen? It will be hanging on y, then x will go this side, and then these two, the concept is that easy if you remember that. These two will be merged. So then the concept is that, so whichever you are moving, so the right child, okay, the condition, there is a condition. The condition is that my right child of x, the right child of x must not be null. If it is null, we cannot do that. It must not be null, right? If it is null, then we cannot hang. It's simple, right? So x as a right child is y. If it is nothing, y does not exist, then we cannot hang on y. Right? So it's straightforward, it is implied. So it must not be null. That means if it does not exist, so there is no node over here from y. There is no node G, right? So we cannot rotate through based on y. We cannot do that because y does not have any child, any node, unless leaf node. Okay, so this leaf, we cannot move through leaf node. You cannot move or rotate through real node, parent node, a parent node. Okay. Now understand? Everybody has any question? Does anyone have any question? We need this. Okay, remember this. Okay. So now, if you understand this, then there is a, it's called left rotation. There is a right rotation. What is that? There is a right rotation. So if you want to do right rotation, okay, so that means what is the condition? What is the precondition for right rotation? Without looking this, please tell me that. What is the precondition for right rotation? The right rotation, okay, right rotation on node x.
That its left child can't be null.
Yes, the right child of y. The right child of the left child of y cannot be null, right? So if it is hanging right now, look at this one. It is it is hanging on point y, but you want to hang on point through x, right? If it is null, you cannot hang on. Right?
And null can't point to anything
No,
else.
it's a leaf. That if it is leaf, that you cannot do it. So these are alpha, beta, gamma means leaf.
Okay.
Need
And
to
those
be.
would all be null, right?
Yeah.
Okay.
Okay. So here then if we want to hang on this, so we want to hang on this, right? So then what will happen? So this beta, okay, so these two, this one and these two will be merged. These two will be merged, right? So this one will be merged. So then how it will be merged? Because y has right child already beta, so that beta it will maintain, okay, and then x will be pointing value, and then x has left side alpha, it will be stay as is, and when these two merges, then this beta will be left child of y. Okay, just you can remember that, just retry over here, the disconnect over here, okay, and then disconnect and then tie it here. Sorry, disconnect here, do the disconnection here. Actually do disconnection for, it was like maybe I can show you, but disconnect here and also here, and then connect here.
I think it would be helpful if you showed like all the steps and like had, looking up at that, like it has 4 steps.
Four
So
steps.
you disconnect the.
Yeah, so that means we will come with algorithm. Algorithm has algorithm. Book has algorithm. If you understand the concept, then you will understand the algorithm.
Disconnect the x and the y.
Yeah.
And connect the. Beta
Connect
and
y,
the
disconnect this one, and then connect with this one. Okay. Visually, if you understand this visually, then it will be easier to understand the algorithm. The book has algorithm. You
Okay.
can see the book, but the book does not depict this way. But I'm trying to explain this way. So now it is a BST, right? So now let us see, there are some examples here. So you see that? Now give an attention here. So as we said that, why do we need to left and right rotation to understand and remember left and right rotation? We know that in Avl trees have 4 kind of rotations, but those are only node to node rotations, right? But here these rotations are not only node with branch, right? So for instance over here, so now this is, so for example left rotate, so you wanna rotate through x and y, these 2 nodes. So why do we need to rotate this? Why do we need this kind of rotation? We need this kind of rotation to maintain color of red black tree that we are going to encounter soon. Okay, for instance here we can move on x and y. So what kind of rotation we need? We need left rotation, right? So in order to do left rotation, we will check, is the right child of x is not null. Is the right child of x is it null? No. It's not nil, right? It has 18. It is very healthy branch, right? It has some children. It's healthy. Okay. So then what we'll do? So then 18 will come up. Forget about other stuffs. So forget about these stuffs. So for instance here. So for now, forget about these and think these are as is. Keep these are as is. So we are think about that these are not here. It will be easy. We have only x, y, we have this one alpha, okay, and we have this one beta, and we have this one gamma. Think about this. On the right side we have the example we showed that we have only alpha, beta and gamma, right? And we have maybe delta and phi. Forget about this for now. Forget about this. Just consider that we have x, this is our x, this is our y, and then we have x has alpha, y has beta and gamma. Because other things will come together, and you can think about that this your gamma has another child. So wherever gamma will go, it will take the child with it. And then wherever beta will go, beta will keep his child with it. Okay, not just for give attention with alpha, beta and gamma. So now, okay, it's working. So we saw that previously, we saw that it was hanging with x. Let us recap the previous rotation. Okay, and x had alpha and y, this is y, and y had beta and gamma, right? So how did we do left rotation? So after left rotation, what did you get? After a left rotation, we got y, right? And x came here, right? And then we got y is hanging on y, and x came here, and then alpha, x has alpha, okay, and y has gamma. And the problem with beta, right? Where the beta will go? So the beta, what did it merge with x, right? Beta merged with x, and then that means we got beta over here. So recall that this is our left rotation effect, right? So that same thing will happen. So here, okay, y will come over here. This is my y, 18, okay, and then x will come here, okay. So then x has what children it has? X has 9, right? Child 9. So then x will come over here, x will come over here, okay. And then let us do the beta, that for sure one, this one for sure, right? So then gamma, this is gamma, this is gamma, and it has maybe gamma 1 or gamma, whatever you think. Cut this one. Okay. So here, when x will come over here, then x has a child 9, right? So this is alpha. This is alpha. You see, this is alpha. This is alpha. And then this is beta. So x right side will get beta, right? So this is beta. Okay. This is okay. I'll move to this is alpha. This is beta. This is x. It has already x. And then how about this part? As I said, they are not going to move, right? They will be as is. Okay? They are there in position. So the concept is like, for instance, you have a family, joint family. You have your grandfather, you have uncles, You have your father and you have your siblings, brother and sisters. Okay, so if you are moving, say you live in a same property. Okay, you are moving, exchanging or swapping your room with your brother or sister room. Okay, and then you are not interrupting your uncles or your grandfather. So this is your uncle, maybe grandfather. You are not interrupting them. Okay, so it's father only can swap or rotate his own children without disturbing his brother or his father, or maybe grandfather. It looks a little bit complicated. Does anyone has any question? Yes.
So if you're gonna ask about these kinds of questions, are you gonna ask like just show the that rotate or like?
Yeah, in the test, are you asking for test or quizzes or assignments?
Either quiz or test.
So first of all, our goal is to understand this concept.
Okay.
Let us understand
When
this.
you do all these cuts and these rotations up high, that shouldn't affect everything down below, right?
No, we are taking everything down with us because we said that gamma is taking its children with it.
Okay.
Okay, then beta is taking its children as is.
Okay.
Alpha is taking its child as is.
So when you're talking about cuts and making new strings, that's just basically deleting and adding pointers, right?
But I said that these are string, right? So I said if you want to do an experiment at home,
Okay.
okay, so draw some piece of paper and then round paper and then cut it, make a hole and then tie with some thread and hang it, and then you'll see that this is rotation.
Like a string? Like a
Yeah, string with thread.
thread and
Yeah,
put
just check the
paper.
thread. There is in cloths of threads, right? And then
Okay.
take some. If you do experiment that way, maybe still if you have problem, then you will understand that.
So like if you put like thread and then like marble and
Yes.
tied them all together
Yes.
and made this and
Yes.
cut them and retied. Okay.
Yes. Understand. Okay. Does anyone has any question about this? Now I'm gonna move for our challenging part, and building an Avl tree. So a red block tree, red black tree. Everybody's okay? Okay, let's go. So this is the algorithm. So it says is the algorithm. It says whatever I discussed, the algorithm says about this. Okay, and the algorithm it says that you see that. So is there any loop? It does not have any loop, right? Okay, that's straightforward. Then running time will be big O(n). Okay, it does not have any loop because it has some if and condition, but this condition do not make any.
Happens once.
Yeah, often happen once. It does not make any loop. Do you know that it is possible to make a loop using just if else without using for?
Wouldn't you need like this jumps and skips, like computer organ R, like you make a loop and then like use a skip and then jump back up to the code?
For instance, yeah, maybe you will understand. Let me give an example. You can write it there. Write an algorithm. You can write the problem. Write an algorithm. Just write it. Whatever I tell you. Write an algorithm to divide a numbers in half. For instance, number is 34. To divide any integer number. Okay. And let us make it out even integer number. Make it divide an integer number without using a loop or without just using simple arithmetic operation. You can do n by 2 is 2 is 16, right? Okay.
So you can't just simply.
You cannot do that way. You cannot do simple math, and you cannot do for loop. Okay. Think about that. Can you do this?
Use while loop?
Yeah, while loop and for loop is loop. You
Okay,
cannot do
so
any loop.
no loops whatsoever.
No loops.
So just ifs.
You can do if.
Just if and then.
Yeah.
So would I just have to say like if? Okay.
It's good thing. Let us do an experiment for this one. Okay. So the question is that, for instance, I have some marbles. Okay, I have some marbles. So n number of marbles. For instance, I have some marbles, maybe n equal to 16. I don't know. Okay, I want to distribute this. I want to make it even, right? Half. Then this side will be n1 will be 8, and this side n2 will be 8 also. So how can I do this? For loop, I can do for I equal to 1 to n by 2. We can move 1 by 1.
So increment one.
I cannot do that way. No, I cannot do increment. That is for loop.
Increment the other one and check if they're equal.
Yep, you are close. So for instance, this side initially n2 is 0, right? And initially my n1 is 16, n equal to 16. I will move one by one item from here to here, and I will check if n1 okay still greater than n2. Okay, then move one item from this side, this bucket, maybe from bucket A. This is an array, A array, and this is maybe B array, for instance.
Wouldn't you increment N2
Yeah.
and decrement
Yes.
N1?
Yes. This is increment n1. Okay. So like increment B, or the put one element to B, right? So there one element to B, and then increment B and decrement A. So then whenever you are moving one item, right? This means move one item. That means move an item from A to B. That will what will happen, right? At some point n on, so you say greater or equal to. Right? So at some point, so you are moving one, another one, then this will be decreasing. So there is no for loop, right? So if condition.
Yeah, but wouldn't you need a loop outside of the if so that you can keep on repeating that statement?
No, that this condition, if condition, will make a loop.
Yeah.
Implicit loop, right? That is, for instance, you are moving one item over here. In real life, we do it this way. How do we distribute? For instance, you have some candies here, right? You are giving equally to your brother. How do you do it? You are giving one by one, taking one from here, right? When you are taking one from here, from your side, and you are giving your brother one, then your brother's side is increasing and your side is decreasing, right? How long you will give? Until you get balance, right?
Yeah.
This is the balance check. Until you have more, you will be giving. So every children do this way, right? We do this way. It's in.
Yeah, but how do you keep on repeating the incrementation?
So here, so until say if condition will do this.
But it's like a while loop.
It is this is loop, internal loop, but this is implicit loop, indirect loop.
Yeah, but where is the
Where the repetition come in?
Yeah, where like how does if you move one, how do you like where is the repeating statement so that you can go and move another? Because that would just move one item and it wouldn't repeat itself.
So the question is like, if you
Oh,
run
where is the
one
looping?
time,
How long?
can you get back to the
Okay, so outside, you got that question. Outside there will be loop.
Outside.
Outside there will be loop. There will be loop. Outside loop will be containing. Outside here.
said there can't be a loop.
No, here is not this loop. I'm saying that you cannot do for loop for equal to inside this loop, inside this one. This for moving, this is no loop. Have you taken like how many of you took programming language construction class or
Concepts of programming?
concept of programming?
No.
You did not take? Anyone took? You took?
Oh,
Yeah, if you take that course, then you will learn that how the programming language actually works.
So don't
How to
use
develop for loop.
Loop for moving, but you can use loop outside of that.
Yeah.
Okay.
Okay, so we have a few more minutes. Let me see if I can complete the insertion. Okay, the insertion operation of a red black too many slides. Let me see which slide is. Okay. Let us try how do we develop a red black tree. First, just we are given some numbers. Okay, some random numbers, and we want to develop a red black tree, so that we have to maintain the 5 properties, okay, of a red black tree. The first property is that, what is the first property? The root is always black. Okay, the root is always black, and if so, the starting point will be to check if the red black tree is empty. For instance, it is empty. Okay, then the element what you will put, that will be root, right? Okay, the insertion, it goes away that whenever you first, anytime if you insert an element, initially it will be red. Initially its color is red, no matter what it is. Okay, so for instance, we got an element, anytime at any element, so maybe 1, so make it red. And if it is the first element and the only one element, that is root, right? So then change this color to black. Then you are done. I have one element. Initially I made it red, but later I saw that no, there is no existing element. Okay, then this is the root, then this is easy, right? Okay, then let us think that, so this is the one, let us think that I got another element. I got another element. So every time we say that, every time we get a new element, make it red. Okay, and if needed, then change color to black, and so that it maintains all the properties. So let us come with an example starting from let us come with an example starting from here. Okay, so initially they could put it in red, but why they put it in I don't see actual color. So make us, for instance, get 1. So let us make it red. So by looking this color, think about the color is red. Okay, since this is the only element, so then change to color black, and this is the root only element. So far I have only one element. Now I encounter 2. Okay, next time I encounter 2.
So why is it red by default?
Anytime if we insert an element in node, it is initially it is born with red color.
So it's default red, and then you change it to black if necessary.
If it is nothing else, if it is, because there is one condition that root is always black.
Okay. So it's red by default, and then if it breaks condition, then you change it to black.
Yes.
Okay.
So now I got another element 2. Okay, 2 initially it is red. Okay. Okay, 2, so you see that a red black tree is a BS tree. So 2 will go right side. Right? 2 will go right side. 2 is greater than 1, right? So 1 is black and this is root, and the 2 we encounter 2 will be right side of 1. You understand why it will go right side? Because it's a BST and initially its color is red. Okay, now we will check all 5 conditions. First condition is that is the root black? Yes. Okay, the last condition is are the number of black in both paths same? Yes, this side 1 and this side 1. Left is null, nothing, right? So we are considering not now, we are not considering the nil or empty, because we can think that there are nils, like 2 has nils and then 1 has nil. Okay, 1 has nil. Okay, and then what is the problematic condition of that? I said number 4.
If a node is red, then its children must be black?
Yes. If a children is red, then both children must be black.
And that would just be 2 nils.
So yes, so does this condition apply here? No. For instance, 1 it is not red. Okay, it is black, so we are not concerned about that, right? And then we say that this is red, and if we imply even the red with the nil, so the nil it has 2 black, right? If it is red, then all children, if it has children, all are black, so it has black. Every node has it has for instance, I could show you like this way. It has a leaf, it has a leaf black leaf, and it has another black leaf, and it has another black leaf. So number of this is black, so number of black in this way 1, and this way 1, this way 1. Okay, a children, if a node is black, then we don't worry. If a node is red, then both children are black. Now it is fine, right? So far it is good, right? The problem will arrive and come then when we encounter more data. I'm sorry. So now we got 3, right? So 3 initially will be 2 we have red, right? 2 we have red, and 3 will counter as red. Initially it is red. Okay, now we will check if a node is red, the problematic condition number 4, right? if a node is red, then both children must be black. So this does not help here, right? That doesn't maintain here, right? Does this maintain? That is a violation, right? So then what we will do? So here we say that we will apply Avl Tree. We have right, then we will do what? We will do right, left rotation over here. So let us make that Avl Tree rotation over here. So we have right, yeah? So we will do left rotation here. So then 2 will come. Let us do 2 will come. 2 is red. I'm sorry, this one. 2 is red. Okay, and then 1 is black, and then 3 is red. Okay, now if it is red, then both children must be black, right? So then 3 we need to make it black. So 3, instead of this 3, make it black. Okay, and then we need to recolor. And then root, this is root, right? Now root needs to be recolor. Then 2 root will be it's easy to use board with different marker instead of changing color over here frequently. So 2 will be now black. So then is an Avl Tree. If it is root is black. If it is black, then we don't care about children, right? If it is red, then both children must be black.
Okay, so it depends on what order we change 2 to become black, of whether or not we change 3 to become black, right?
Sorry, this question. What is your question?
So we changed 3 to become black because 2 was red.
Yes.
Right? But what if we change 2 to become black before that because it's the root node? Then
we need to do both. So that is sequence is not matter, but we need to do both.
Okay.
So here the color we are recoloring, right? 3 was red. Initially it was red, right? So maybe you can do that before rotation.
So what rule did we violate to do the rotation in the first place?
So in the first place, before rotation, what did we violate?
Yeah, what did we violate?
So first of all, we did 2 kind of violation. For instance, it was not a balanced, height balanced, right?
So condition.
This side is height is 0 and this side height is 2. The difference between is.
Well, I thought that was for the
Avl Tree.
Avl Tree.
This is implied here. I said Avl Tree. All Avl Tree is implied. All rules of Avl Tree is implied here.
So all red block trees are Avl trees. Okay.
So then it is violating color and also height. Okay. So this is why we, in order to maintain height, we do rotation, and in order to maintain color, we do recoloring. Okay. So I will upload these slides in D12, and then please come to the next lecture. At least please look at this. Okay, the insertion operation, because deletion is more complicated than insertion.
So, can I just take one more look at this? So when you did the rotation, you just made everything black, right? Like the previous slide that we did the rotation.
So for the rotation, whenever we do rotation, keep color as is.
Okay.
Then change color.
Okay, so then it would be 1, 2 red, 3 red.
Yeah, 2 red and 3 red.
And
Then
we'd have to make the 2
then-
black because it's the root, right?
change the root, then make it
You since
black.
choose the root and make it black. Then you
And
have
since this one, what is that one? So initially we need to change this one, since you cannot have, you need to change 3 first. Or you have a question that one, like 3 first, because it will violate the color, right? It will violate the color. So for instance, so red. So because it is 2 has already one black. This side is black, right? The leaf, empty leaf, nil leaf is black. And then whenever you make it black, initially you insert as red, and then quickly change. Next step is change it. When you check the color, change this to black. Then it will come in black, and then later you change it. Maybe I can write like show this way. This one is red, and then after this one, maybe we can do another way. This one, change this color too.
So first you change the 3 to make all the paths have the same number of, like, all, so that's
It
dividing
is
every
not.
path
No,
has-
no. You cannot check path over here, because until you make a red black tree, the path will not be maintained. Here it path maintains.
Okay, so
Number 2.
you change-
Here it is not completed. This is incomplete. This phase is
Okay.
incomplete. Even this phase is incomplete.
Okay, so you do the rotation, then you start checking conditions.
Maybe I'm doing one more thing. So I'm doing
Okay.
this one. So let me do this one. Maybe it will help you to understand. So if I do another picture, the step 1 over there, step 1 that, this is step 2. The step 2, in the step 2, this is step 2. Step 2, this will be black. This is step 1. This is step 1. Let me color it.
Oh, because that was already black because the red's child must
Yeah.
be black.
So this one step 1.
Okay.
Step 1. This one step 2. This one step 3. And this one step 4. And this is red. This is red black. Take a picture. Yes.
I have it all written down. Luckily, I have red and black pens.
Oh, that's good. That's good. Thank you. Yeah, I should bring that one and then.